Uh, so Xianghu is a first-year PhD student at UC Riverside, working with myself, and so he's been exploring some of these challenges with molecular networking construction. And to be honest, the funny thing is, the things that he's improving on, these are things that we never really tried, formally doing this scientifically. A lot of the things in GNPS, you'll find this out in creating molecular networks, they were done because they were easy and obvious, and we didn't measure them at all. And so they were unscientific. And so Xianghu has taken the time and taken the intellectual effort to try to understand the real problem and try to tackle it from a principled computer science approach. And we think it makes things better, but I'll let Xianghu explain what he's been working on with molecular networks and transitive alignments. So I'm very proud of the work that he's done, and I'll let him take it away.
Okay. Thanks, Professor Ming, for the wonderful introduction. And hi, everyone. I'm Xianghu. And today I'm gonna talk about the molecular network benchmarking and the transitive alignment workflow. So before we dive into the actual content, let me lay out the main point and the highlight of the today's presentation. So first, we will propose matrix to evaluate the construction of molecular networks, and then we will benchmark common approaches for molecular network. And we use some insights from the benchmarking. We propose a new method to construct the molecular networks. And the proposed transitive alignment method can improve the state-of-art network construction method performance by over 30%. And the new molecular network construction workflow is now available on the GNPS2 platform. And so since it's VMOL similar, so today I will mainly focus on the method of transitive alignment and how to use that workflow, and may not go through very detailed about the benchmarking side. So first thing first, let me refresh some common ideas about molecular networking. So molecular network is a powerful computational tool to visualize and analyze the tandem spectral data we have. Here is one of the molecular network we constructed on the GNPS2 platform. And if we look at and zoom into this part, we can find one of the important features of molecular networking is it can organize the similar molecules into similar families. So it might potentially give us some insights across the whole chemistry space. And at the very first point of molecular network is we just want to answer a very fundamental question about how we compare, how we tell how similar two molecules are. And one of the most canonical way to do this is we're leveraging the spectral similarity to infer the actual structure similarity. And nowadays we have these very well-developed tools can do these things. And having these things in mind, the next step we want to do is we want to know how the all the molecules in our data set and how to organize them into different families. And that comes to the molecular network. So in the first step of constructing the molecular network is we calculate all pairwise cosine similarities across the whole data set, and we set a certain threshold to filter out the low cosine score edge, and it will usually result in a network look like this, and we call it row pairwise network. But just have the row pairwise network, it's just it's very hard to tell which part of the molecules in this network belong to the same family. So the next step is very important. So we have these filtering algorithms to apply on the row pairwise network to create actually usable networks. So the goal of the filtering algorithms is first for the human integrity and reduce the false positive connections in the molecular network. Now, next question comes to us is this construction of molecular network actually good? So if we take this part of component from the whole network, and if we focus on this pair of nodes I circled out, and when we look at their structure, actually, it's not that similar. So it means that the filtering algorithms not always accomplishment our goal. So we need to have some metrics to evaluate how good the filtering algorithms works. And when we design the metrics, we most focus on two aspects. First is how accurate the network is. So here we want a matrix to reflect the actual structure similarity across the whole network. And another aspect is how complete, or obviously how large the network is. So basically, for example, here you can have different constructions for the filter network based on the same amount of data. And on this lower right corner, you can have this very fragmented construction, which only result in full pair of nodes. And you can also have a construction like in this upper right corner is very complete and have these big components. And we prefer this the construction like in this way because it can potentially give us more information about the molecules in the data set. So let me first introduce the matrix to evaluate the correctness of the network. So we use the structure similarity at the edge score, but based on the filtering algorithms to calculate the component accuracy score. And then we put this component back to the whole network and aggregate the component accuracy score to get the final network accuracy score. So here the network accuracy score is a score range from 0 to 1, and a more higher value means it's more accurate. And next is the matrix to evaluate how complete the network is, and we call it nth number. So we get some inspiration from the genomics side. So, but what we do in our molecular network side is we first sort the whole network based on the number of nodes in each component from the largest to the smallest. And we add up the component size until it reaches to a percentile of the whole network. And the number of nodes in the last component we add up to reach to a percentile of the network. And we call it the nth number. And in practice, we use N20 as our measurement. So here, a more higher value of N20 means the whole network construction is more complete. Now, having this matrix, we want to evaluate and benchmark the performance of the existing method. So we first benchmark these two methods. The first one is the baseline, so which means we don't do any filtering algorithms on the network. It's just row pairwise network. And the next one is the classic method, which is widely used on the GNPS, and also I think it's the default setting for the GNPS2 platform. And here is the result for these two methods. So here the x-axis is the N20 number, so which means the larger the better. And the y-axis is the network accuracy score, also the larger the better. So the right improvement direction is toward this upper right corner, which means we have a large component size, but also maintain a relatively high accuracy score. And a point of scale plot here means a specific parameters for each method, for both methods. And we can see very clearly that the classic method will performs better than the baseline method here. And next, we want to test the pseudo-click finding. We call it the CAS algorithm. So let me give a very brief introduction of the click finding, this CAS algorithm. So first, a click means a subgraph in which nodes are directly connected to each other. So like these structures in the component, we call it click. And the reason why we want click finding is, so the molecules from the click structures are more confident that they belongs to the same memory because they connect to each other. So here I plot the CAS algorithm results on the same plot. And you can see it's very clearly that the CAS algorithm for the small component, the CAS algorithm can give a very accurate construction, but it's false in extent to large component. And the reason why this happens is we find there are some limitations of the modified cosine score calculation. So for example, here, if we have two molecules and they have only one modifications, and how we use the modified cosine score to align, to calculate the similarity of these two molecules is we use a technique called shift alignment. So we know the precursor mass difference of these two molecules. And if a peak is shifted near the mass of these delta modifications, and we will align these peaks together. So if there is only single modifications happens, the modified cosine score can perfectly align and calculate the cosine score. But if there happens to multiple modifications, more than one modifications on different sites, for example, here we have delta and gamma modifications on different sites of these molecules. So in this case, we only know the precursor difference of delta plus gamma. So in this case, the peaks can shift either delta or gamma. So in this case, we can't use the precursor mass difference to align the shifted peaks. So in this case, we will propose our method, which is called the transitive alignment to solve this issue. So we get some inspirations from genome, from proteomics, and we will use the network to solve this problem. So since we can't align, so for example, here we have molecules A, B, C, and A and B have two modifications, delta and gamma on different sides. And we can't align them directly, use a shifted mapping method. But if there exists a molecule C in the network, and A and C, the only differs by one modification, and C and B, the only differs by one modification. So in this case, we can use the shift alignment to align the peaks from A to C and C to B. So we know which peaks, in this case, we know which peaks in A can be aligned to the peaks in B here. Right. So now, and here is the whole process of the transitive alignment algorithm. So our goal is to align two molecule or two nodes A and B here, which is they are not directly connected, but there is a path from A to B. So first we will using the single source shorted path algorithm to find the path with minimum hops between A and B here. And if there are multiple passes have the same minimum hops, and then we will use a path that has the maximum sum of cosine similarity denoted at the K path. And we will use all the nodes along the K path to realign node A and B. And here I will choose a concrete example from our benchmarking data sets. So we have these X, Y, and Z molecules here, and I choose the structures of each molecules above the node. So we can see initially the Y and X only differs by one modification, and Y and X, Y to Z differs by one modification, and Y X differs by one modification. So the modified cosine score between Z and Y is very high, is 0.9. And also for Y and X, they are very high, about 0.8. But since Z and X, they have two modifications on different side here, the original cosine score is 0.09. And if we look at the aligned spectrum from X to Z, they can only align 3 peaks here. And if we're using the transitive alignment to align Z and X through the intermediate node Y here, we can see it aligns all the peaks, the mean peaks from X to D here. And we can see the transitive alignment cosine score is now reached to 0.8. And if we look at the actual structure similarity score from V and X, they are 0.77, which means they are similar structures. Now I want to demonstrate how the transitive alignment can improve the filtering algorithm like CAST algorithm. So suppose here we have the RoPyOS network, and all the molecules in this network have similar structures. And an edge exists between 2 nodes, means a high cosine score and a single modification. So if we just apply click finding on this network, it will only identify 2 small clicks, right? So it's click A and click B. And then if we use the transitive alignment method, so it can use a path between 2 indirectly connected nodes to align spectra due to modifications and rebuild the edge between them. So here's the dashed line means the rebuild transitive alignment edge. So in this case, if we do the CAST algorithm based on this newly network topology, we will find that the CAST algorithm can now identify a larger clique which have all the nodes in this clique. Here we denote as the clique C. And next, I will show the CAST plus transitive alignment result on the same plot as previously. So we can see that it improved. It had the best performance among all the existing method here. Okay, now next, let me introduce the transitive alignment workflow. So the transitive alignment workflow is now available on the GNPS2 platform. And now you can run the transitive alignment workflow as a downstream analyte of classic molecular network or run it independently here. So if you click this button in the classic molecular network task page, then you can just directly run the transitive alignment workflow as a downstream analyze. And we recommend you to do this way because the transitive alignment workflow itself will not have the library identification and MS clustering. So if you run transitive alignment as a downstream analyze, so it will automatically select all the files. Otherwise, you need to import them manually from the classic DAG workflow. And for the workflow, there are 2 options. The first one is the full network transitive alignment. So if you select this option, and this will only make the parameters in this circled area take effect. So basically, if you choose this option, it will run transitive alignment for the whole network. And then it will use the CAST algorithm to filter the network. And here is about the parameter setting. So the minute click cosine score here means the score threshold for each component in the for the CAST algorithm. And this minimal transitive alignment score means the score threshold for adding back a transitive alignment edge. And the MST filtering option here, basically, we use the maximum spanning tree to better lay out for each component. And there are 3 ways to do the layout filtering. So the first one is the pure MST, which is just using the MST based on all the edges. So which means it's use original plus the transitive alignment edge set to do the MST. And for the greedy MST, it will use MST plus the greedily add back edge to get the maximum average score topology for each component. And the hybrid MST, it will only use the original edge to construct the MST. So, and if that fails, then it will greedily select the edge in the transitive alignment set to finish the MST. And we recommend to use the hybrid MST because the edge we use in the hybrid MST is more reliable than the other method. And once you finish setting all the parameters here, you just submit the workflow, and you can visualize the results as the same as the classic network topology, the same as the classic network flow. And next, I want to introduce the induced network. So the induced network, it will induce a network from an interested target node based on the maximum hops, which indicates the maximum number of structure modifications and the transitive alignment score. So for the induced network, it can better use the transitive alignment method and will get more accurate or complete subnetwork if you have a interested target molecular in the data set. And how we use the induced network is, so first you need to select the induced network option. And if this option is selected, then only the parameters in this area will take effect. So it will induce the network from the target node using two methods, the intersection or union method, and I will introduce them later. So here is the parameter settings for the induced network. So first, here's the induced network, the source node, which is the target input source node that you are interested at. And here the max hops means the maximum number of hops from the target node. And the minimum transitive alignment score, which is the same as the network topology parameters, it's a score threshold for a transitive alignment edge to add back. And the MST filtering options is also the same as the MST filtering options for the network topology. So here I will give a brief introduction about the introduction and the intersection and union method to induce the network. So if we set the max hops equals 2 and add back edge score to 0.6, so first for the intersection method, it will select the node within 2 hops from the source node. So here the orange denote as the source node, and the yellow one is the selected nodes within 2 hops from the source as a target node. And we also do the transitive alignment from the source node to all the other nodes in the network. And we select the nodes that have a transitive edge that is above 0.6, the setting threshold for the transitive alignment set. And then we do an intersection of these node sets, the yellow node set for these 2 steps. And here we get the final topologies here for the intersection method. And for the union method, if we use the same settings here, which is maximum hops equals to 2 and add back edge a score set to 0.6, so it will first it will do the same thing. So it will use the transitive alignment from the source node to all the other nodes, and add back the edge above the threshold and select the nodes within 2 hops based on this topology. So in practice, we recommend you to use the intersection method because it will only take the node if and only if they have the transitive alignment score above the threshold and also gets the maximum hops limitation. So that's the recommend method here. And next, I wish also here is another thing I need to mention is for the induced network, there is a transitive pairs list, which is help to interpret the transitive alignment process. And next, I will use a very concrete example to how we use this the transitive pairs list. So for example, here we create a induced network from a source node. Here, the source node is 261. And if you take a look at the trace pairs table, so basically here, for example, if the source node is 261 and using the, in this rule, we can see it will align the target node 106, use this realigned path, which means it will use the intermediate node 210 to realign the node from 261 to the target node 160. And it will increase the original sign score from 0.2 to 0.8 here. And here is the links for this demo task here. Okay, that's all my presentation today. Thanks for listening. And any comments and questions are welcome.
Okay, awesome. Thanks so much for the very insightful presentation and views into like the transitive alignments. We will open up the room soon for questions, but yeah, before I just want to say thanks everybody for stopping by, and I'll stop the recording in a second and hope to see you all in 2 weeks with Helena and like the knowledge database of the CMMC.